Hi friends, welcome back to Muendamberi Academy. Today we are going to revise a chemistry specimen paper 3. So we are going to answer the first question for section A. So I have just extracted the whole part of the question number 1. So without wasting our time, let's watch. So this is our specimen paper, ZIMSEC A-Level Chemistry Revision Specimen Paper 3, Section A at 2026. So the first question on part A is saying the isotopes of copper and their relative abundance are shown in the table 1.1. So this is our table, and the following question is part 1, part 2. Then we also have part B with item 1 up to item 3. Then we also have part C from part 1 up to part 3. So for the whole question, it's awarding 15 marks. So we don't want to lose any of these marks. So let's dive into the working. Right, so for the first question, it's saying the isotopes of copper and their relative abundance are shown in the table 1.1. So this is our table 1,1. So here we have got the isotope, and on the right side we have got the height on the graph in centimeters. So for the copper isotope 68, it has got a height of 7 centimeters. Then another copper 65 has a height of 3 centimeters on the graph. So the first question is saying define the term relative isotopic mass. So to answer this question on part 1, so relative isotopic mass, this is the mass of one atom of a specific isotope here measured relatively to the mass of carbon 12. Okay, so that's the definition for the relative isotopic mass. So for the first part we are done. So the second thing we have to calculate, which is the part 2, we have to calculate the relative isotope atomic mass, which is AR, of copper. So from this table shown on 1.1. So to find the relative atomic mass, generally we say the AR1 multiplied by the relative abundance for the isotope 1, then plus the relative isotopic mass of another isotope, then multiplied by the relative abundance of that isotope, then all over the total relative abundance. So that's the general formula. So we now substitute. So our relative abundances are given in terms of height. Then the relative isotopic masses are shown here. We have got 68 and 65. So now I can say for copper 68, its relative isotopic mass, I can say 68 multiplied by the relative abundance, which is 7, then plus the relative isotopic mass of another isotope is 65, for copper 65, so I write 65 multiplied by the relative abundance given here is 3. So all over the total relative abundance. So if I add 7 and 3, I get 10. So which is 7 plus 3. Then here I can, since it's paper 3, we make use of a calculator. So I'm going to calculate these values so that I will get a correct solution for this part. So 68 by 7, 68 by 7. So this gives us 476. Then plus 65 by 3, 65 by 3. This gives us 195. All over 7 plus 3, we get 10. So if I add the numerator, 476 plus 195. So this gives us 671 over 10. So as our final solution, if we divide this by 10, we get 67,1. So this is the relative atomic mass, okay, for copper. So we have managed to answer the part 2. Right, so we are now moving on to part B. So part B, item 1. First we have to understand the demands of the question. So it's saying define the term lattice enthalpy. So lattice enthalpy is the energy released when one more of gaseous ions combine under standard conditions. So that's our definition: the amount of energy which is released when one more of gaseous ions combine under standard conditions. So we can move on to part 2. Then the part 2 is saying state and explain 2 factors that affect the magnitude of lattice enthalpy. So the first part we have to state, and after stating we explain. So the first factor which affects the magnitude of lattice enthalpy is ionic size. So as you can see, I have just stated the factor that affect lattice enthalpy, or the magnitude of lattice enthalpy. So the second thing is to explain. So how does the ionic size affect the magnitude of lattice enthalpy? So increase in ionic size decreases. The strength of electrostatic forces of attractions, and also the magnitude of lattice in the. So that's how ionic size affect the magnitude of lattice end-up. So as ions become larger, they attract or they approach less closely, hence the lattice end-up decreases. Then the other factor is, so I've just mentioned the ionic size. Then we have got charge density. Charge density. So when we talk of charge density, to those who don't know what it means, we say the amount of charge per area or given volume of an atom or ion. Okay, so increase in charge density increases the strength of electrostatic forces of attractions, and hence increases here magnitude of lattice end-up. So those are the factors. So as you can see, I have stated and explained the factors. So now I'm sure that I can collect those marks on that part. So we are going to move on to part 3. So we are going to move on to part 3, and it's saying explain why the hydration enthalpy of magnesium 2 plus ion is negative 1927 kilojoules per mole, whilst that of sodium ion is equivalent to negative 406 kilojoules per mole. Then yeah, that's the question. So it's like we are just comparing the sodium ion and the magnesium ion. So with reference to their respective hydration enthalpies. So as we saw earlier on part B, so we say that the factors that affect the magnitude of lattice enthalpy are ionic size and charge density. These factors also contribute to the hydration enthalpies because we deal with the electrostatic force of attractions. So what is different in magnesium ion and sodium ion? So we can say that this hydration enthalpy for magnesium 2 plus ion is more exothermic than of sodium ion. Okay, right. So the reasons we say, the first thing we have to state the differences. I can say magnesium 2 plus ion has a greater charge density. So now the difference is on charge density, the amount of charge, which is 2 plus. So this is greater than 1 plus for sodium ion. So magnesium 2 plus ion has a greater charge density as compared to sodium ion. Okay. Hence, a lot of energy is released when Mg2 plus ion is hydrated than hydrating sodium plus ions. Okay, so these are the differences. So I just explained the reasons why a magnesium 2 plus ion is a more negative hydration end up than the sodium ion. So for part B we are done. So let's move on to part C. So part C, item 1 is saying state the 2 conditions for the formation of hydrogen bonding. So they are not saying, or they are not asking for the conditions like temperature, pressure, catalyst. Those are the conditions which are mostly asked by some questions in your papers. But here you have to take note, because when we talk of hydrogen bonding, they are saying what should be there for hydrogen bonding to exist. So we can say there should be, atoms or 2 atoms with a great or a greater difference in electronegativity. So we can just shorten it as greater electronegativity difference. So you can say should be 2 atoms with a greater difference in electronegativity. For example, let's say there is an hydrogen atom and a nitrogen atom. So the 2 possess a greater difference in their electronegativity values. So a hydrogen bond can exist. Or we can talk in terms of, we mentioned the aspect of electronegativity. The other condition, we can talk of lone pair, the presence of lone pair. So presence of a lone pair of electrons on one atom. So these are some of the conditions which can be mentioned on part 1, because they just need 2 conditions. Then we are done on part 1. Right, so for this part we have to be very, very careful we are going to sketch a graph. So it's saying sketch graphs of PV against P on the same axis to show how the following gases deviate from ideal behavior. So we have gases NH3, carbon dioxide, and helium. So NH3 is ammonia, and you have to know the chemistry of these gases before plotting the graph or sketching the graph. So let's see. All right, so our question was saying sketch graphs of PV against P on the same axis to show how the following gases deviate from ideal behavior. So the gases are ammonia, carbon dioxide, and helium. So among these gases, we can say that helium is in group 8. Okay, so helium, we know it. Then carbon dioxide, there is bonding. Okay, then in ammonia there is bonding, so automatically we know the forces of attraction in each gas shown. So we want to know how to sketch them on the same axis, but we actually know that the graph of PV against P, which is pressure and the product of pressure and volume at a certain temperature, they have a certain behavior, the ideal gases. So it's constant like this. So we want to know how these gases behave. Do they behave likewise or they deviate like? So that's what we want to show. So we'll start with the helium gas. So I will show its graph with the red pen. So helium, it goes like this. It slightly deviates. As you can see, as pressure increases, the deviation also increases. So it deviates more when pressure is increased. Then this one, I said this for helium, so I can mention it here. Helium, or as shown, can just say He like this. Then for carbon dioxide, so in carbon dioxide they are covalent bonds. Okay, so they are just bonds in carbon dioxide, but we know that in ammonia they are both hydrogen bonds and they are covalent bonds. So which means in ammonia there are stronger forces of attractions than in carbon dioxide, but the forces of attractions in carbon dioxide are greater than or are stronger than those in helium. So we expect the graph of carbon dioxide to deviate more from ideality than helium. So for carbon dioxide it looks like this. So this is for carbon dioxide. So this is above that of helium. So for the last one, right, which is ammonia, this one deviates the most, okay, from ideality than other gases. So can show it like this. So you can see it deviates more from ideality. So this one I can say this is for NH3, which is ammonia. So that's the graph. I have clearly sketched the graphs, but when you draw in your exams, you make sure that you use a pencil, okay, but here I'm just using the red pen and blue pen so that you can actually see the differences on the behaviors of the gases. So for the last part, which is part 3, they are saying explain the difference in the graphs. So we want to explain why the graph of helium like this and for carbon dioxide like this. Okay, so as you can see that helium, so we start with helium. So the graph is saying it deviates the least from ideality or from ideal behavior. That's how the graph is showing. So the graph is just showing this information. So the reason, so we can say because there are only van der Waals. They are just van der Waals forces of attractions. So that's the reason. Okay, so we can also talk about carbon dioxide, okay, because we have to explain each graph. So for carbon dioxide, so that was for helium. Then for carbon dioxide, so deviates more, so I can just say more from ideality because of strong covalent bonds present. So in carbon dioxide, there are covalent bonds between carbon and oxygen atoms. Then lastly, we want to explain the graph of ammonia. So NH3, so this one deviates the most. So deviates the most because they are both covalent bonds and the hydrogen bonds So that's it. We have managed to answer the first question, which is number 1 for the section A of a specimen, paper 3 chemistry. So yeah, that was the paper. I hope you find this helpful if you follow each step from number 1 solutions up to which is on part A up to part C. Yeah, that was the solution for each and every part. So if you find this question and solutions helpful, please like the video, comment, and don't forget to subscribe. Alright, so as you saw, each step or each question is its operation and you have to understand the question first so that you can answer the question correctly. So guys, don't forget to subscribe so that you see more videos. As I promise, in the next videos you will see some solutions of other questions in that paper, because we just answered the question 1. So there is question 2, question 3, so on. So don't forget and to share the video to others so that they can find this helpful as part of their revision. Thank you.